The teaching profession is something which I like very much, because I feel teachers can do a lot not only in teaching but in making students interested in the subject. Because I personally feel whenever I look back, if I have some interest in some specific topic, it can be traced back to the teacher or the teachers or the gurus who have taught us in school or college. Anyway, today we'll talk about the space technology and in the space program. Maybe you all are aware, ISRO is under Department of Space, and under that there are many autonomous as well as other bodies like Physical Research Lab, NAR, NISAC, Semiconductor Lab. Now it is CLS moved to MIT. There is an institute, IEST, and the commercial arm of ISRO, Antrix, as well as NCIL is again a limited company dealing with getting business for us. And you also know, thanks to the reforms for inducting more commercial parties into this program, okay. We have a mechanism called InSpace, that is a single window system, and that is also in place. We hope we will have more startups, commercial firms, and other industries coming forward and participating in the space program. You know, it's a huge business. $400 billion is the type of number we are talking about, whereas our contribution is very, very small. So we need to enhance it by suitably augmenting commercial presence also. So there is ISRO, Indian Space Research Organization. Under that, there are different centers. Vikram Sarabhai. Okay, I was talking about the organization structure of ISRO. There are centers like Vikram Sarabhai Space Center in Trivandrum it's called the mother center of ISRO because, you know, Dr. Sarabhai came there and that was the first center. And all the other centers got evolved from VSSC, like Liquid Propulsion Center in Adiyamala, Trivandrum. Satish Dhawan Space Center in Sriharikota, that is our launch port from where we are launching. IIRS Rao Satellite Center, or earlier it was called ISAC in Bangalore, where they make satellites. Space Application Center in Ahmedabad, they deal with payloads, applications, and many other technology development. NRSC and the new center is Human Spaceflight Center, dealing with Gaganyaan and human spaceflight. Under that, there are other small units as well as like IPRC, IESU, LEOS. Small, it's not in terms of what you call technology, but it's only in terms of number. But they are also playing a vital role in making important system, like IPRC is doing all the assembly integration of stage, whereas ISC is making so many inertial sensors. Like that, this is the overall layout of ISRO. And if you see, this is how ISRO is represented. You can see it's just got a pan-Indian presence, are shown here all over the India, and with the headquarters at Bangalore, where ISRO Chairman Secretary DOIS is sitting. So this all started with space research under Department of Atomic Energy, which was headed by Dr. Sarabhai. In 1961, we can say this is one area which we have not missed, because 1957 was the first launch of Sputnik by the then Soviet Union, and we have started our program in 61. Then we started with the Indian National Committee for Space Research, which has later become the ISRO as well as and the Department of Space. So there is a Space Commission, that is the highest body under Prime Minister's office, where all the major policy decisions are taken. So we can see this is how this organization got evolved from 1963, Vikram Sarabhai Space Center. There is something called a Tumba Equatorial Rocket Launching Station, which is a place where all countries can come and do research. Then URSC in 72, LPSC formed in 87, ISU in 1990, IIST, the institute, as well as HSFC, the youngest center, in 2019. So if you look, we have more than 177 missions. And if you look at the vehicles started from SLV, for which Dr. Kalam was the project director, then augmented satellite launch vehicle. These two vehicles are not in production because they were basically technology development. But we have now PSLV, GSLV as well as GSLV Mark III. PSLV had so many flights, okay, 39 it is written, but just got more than 50 flights. And we have more than 102 satellites, many experimental missions, satellite missions, like we can say 270 plus satellites from more than 33 countries we have launched. We give a very affordable launch opportunities for many countries. So we have a very important area is space applications, because when the program started, Dr. Sarambhai's vision was our program should be for common man. So the space application is a very important aspect. Space commerce, of late, maybe last 1 decade or so, we have a special arm for space commerce, because business, they create business opportunity, and we have the capacity building in different domains. Space transportation, that is how we take satellites to space or to other planet, and then infrastructure like launch pad or tracking or whatever ground system we want. So these are all the different domains or major subsystems. This is, I was telling, this is how we have grown from SLV to GSLV. GSLV has a lift-off mass of 644 tons. You can just imagine 644 tons, and whereas PSLV has something like 295 tons, and it is something like a 15-story building height. It may look like a pen here. It's a huge structure, and rockets are designed like this, which has got a large structures with the propulsive system. Satellites will be at the top. So the idea of a satellite is to cross the atmosphere vertically and then give velocity to the satellite and then take it to a correct orbit with the required velocity. Because in order to stay in an orbit, you need a minimum velocity corresponding to the altitude. So it is done by the launch vehicle. Once it is done, launch vehicle's job is done. Then the satellites, it has got its solar panel, its power systems, and that satellites will collect data and then send to us. So looking from above has always an advantage. We know that in all times, soldiers, they used to climb over the say fort or something like that to get a farther view. View from top will always give you a broader view, like a eagle is looking from top for its prey. It's looking from far above, and it has a very sharp eye for sensors, and when it detects its prey, it comes down. So something like this, we go up and then look down with a very powerful sensors and see broader areas and then collect data and use it. So PSLV is still going good. We have the next launch in June. It's a fully commercial launch. It's a very highly versatile vehicle because we have done many types of missions with that. It can go to low Earth, it can go to polar orbit, that is around the polar poles. It can take satellite to geosynchronous orbit, that is 6,000 kilometers. It has taken payloads or satellites to Moon and Mars. Both our missions were done by PSLV. So it's a highly flexible mission, and it has even launched 104 satellites in one mission. So it's a very vehicle with now so many launches are planned with this. Similarly, GSLV, which has used first time cryogenic propulsion, we know that we wanted to get it from abroad, but then it was just not very successful. So we designed our own cryo system, and it can take something like 2.2 tons to 36,000 kilometers. So you please understand these orbits are very important. Usually for remote sensing, you go to a polar orbit. From that below the orbit, Earth will rotate, and you can always observe the Earth. But for communication, we go to 36,000 kilometers. Advantage is when at 36,000 kilometers, the orbital speed of satellite and the rotational speed of Earth both are same 24 hours. So a satellite will be always available over our country. So for communication purpose, we always want satellite over our own land. So that is the difference. So it can take, GSLV can take 2.2 tons to GTO. And you can see this is how the launch vehicle. This is the first stage, a central stage, which is a solid propulsion. And VSSC is an expert, has a very good expertise in making world-class solid motors. Around that, you have 4 liquid straports. And then there is a second stage, again a liquid stage. Third stage is the cryo. So it's a huge activity. It takes around 45 to 50 days to assemble the vehicle. You can see the tilting operation. There are inter stages. There will be kilometers of cables running from vehicle top and bottom. Just got its own avionics. You can see there is a people are standing there. You can see the size of it. You can appreciate. And then we do the assembly. When after assembly, it looks like this. We then move to the launch pad. Here you can see far away, very slowly, maybe 1 kilometer takes 1 hour. And then you fill propellant, launch. Then came Mark 3 or LBM 3. It's the most powerful vehicle. It's a simple vehicle also. You can see 2 solid motors. And there is a same Vikas engine, we call the liquid engine. And another Indian cryogenic engine. So it's only a 3-stage vehicle, which can take 4.3 tons to 36,000. And same vehicle, if you go to say 400 kilometers, it can take more, or that is 10 tons. That is why, because of its simplicity and the payload capability, this vehicle is selected for a Gaganyaan mission with a suitable modification. And the same vehicle is used for the Chandrayaan 2 mission. That is going to, then the next Chandrayaan also will be launched by this. You can see the Chandrayaan is getting assembled and then launched. Now, this I was telling. For the Gaganyaan, we are converting this vehicle. The top portion, that is pairing plus satellite, is replaced with an escape system, and inside this, the crew capsule will be there. But you can see the lift-off mass is 645 tons with this 51-meter height. It's a huge vehicle. So we, for human-rated mission, we do many things because safety is important. So we add more redundancy. Instead of dual avionics, we make it quadruple. There is a very powerful fault detection software with so many sensors running in redundant mode, 3 sensors for each parameter. These sensors will collect data and then say any system is malfunctioning. If it is malfunctioning, then the escape system will be activated. That will take the crew away from the vehicle, and then they will be bailed out. So this vehicle is also in the final stage of realization, and we are going to have the first unmanned flight soon. And another interesting thing, you know that there is a worldwide, there is interest in small satellite because everything is becoming small. So we are making a small satellite launch vehicle. Its first launch will be end of June from Sriharikota. It's just 2-meter diameter, all solid stages with a payload of around 500 kg. It can go to 300 to 400 kilometers. The advantage is a simple vehicle, all solid stage. Idea is we will have 1 or 2 missions or 3 missions, and then we give to industry. Industry, they can form consortia. They can, through NCIL, they can get satellites from other countries and make money. We give other support like the launch support and other things. So this, we are going to have the vehicle soon. But then we also know, if you want to be competitive, your cost has to be reduced. If cost can be reduced, one way is we again and again reuse it. So this experiment we did some time back in 2016. A winged craft was taken to a hypersonic condition. Hypersonic means it has got more than 5 times speed of sound. You know, when a vehicle is entering from atmosphere into atmosphere, I mean from a space into atmosphere, its Mach number or the ratio of its speed to the local sound is something like 25. It's flying at 25 times speed of sound. So we reduce the speed and then make it come and land. So this experiment will be successfully done. Again, next week we are going to have an important experiment where this first time we are going to land on a runway with a very high speed of the order of 95 to 100 meters per second. That is something like 360 kilometers per hour. You know that a fighter aircraft is landing at something like 65 to 70, whereas a conventional transport aircraft will be still lower. So this is a very high speed landing. It's a record breaking speed. We will be landing and demonstrating high speed landing with landing gear system and other system, which we will be doing from the DRDO landing strip at Chitradurga in Karnataka, maybe end of this week. We are targeting if climate weather conditions are good. But then again, you know that oxidizer is an important part which we are carrying when we go to space, because space there is no medium. But when we cross the 100-kilometer thick atmosphere, idea is that can we use the oxygen available in the atmosphere? We have done one experiment, as you can see here, with a small rocket, which will fly at very high speed and collect air from atmosphere, and that air is used as oxidizer. Buoyed by that success, we are planning another experiment where this will fly for around 500 seconds. It will collect oxygen from atmosphere, burn, and then acquire velocity and then go to space. So this is one experiment, new area where we are working on. At the same time, we want to reduce the speed of re-entry body. One option is we can have inflatable aerodynamic decelerator, which will be folded initially, and when you come back, you inflate it, and then you are not allowing the bodies to accelerate by the drag on the body. So this experiment using a sounding rocket, we are planning that will be done maybe in another 2 to 3 months time. This, if demonstrated, this technology can be used for recovering the stages of rocket after it has been separated from the vehicle while re-entering. You can just inflate decelerators and collect it. So there are different class of satellite. Communication satellite, as I said, at 36,000. Navigation satellites for giving you Google type of guidance, like the Navic system. There are many Earth observation satellites for remote sensing and so many other applications, forest conservation or water bodies, or so many applications are there. Then we have science missions to Mars, Chandrayaan, and then there are even AstroSat. There is a mission to Venus is also being discussed. There are high throughput satellites, how your satellites efficiency can be increased, direct to home satellites, multi-beam S-band satellites. So many technologies are getting tested in satellite area. As I was telling, Aditya L1, this Lagrangian point in space, there are 5 Lagrangian points. These are all points where you get zero gravity conditions because the body forces will be balanced. So we are taking one satellite to L1, that is something like 1.5 lakh kilometers away from Sun, and put as observatory and then observe the Sun and its corona and its different radiations and other things. Similarly, Chandrayaan-3, last we had some problem towards the terminal phase, but Chandrayaan-3 is getting ready. And there are other satellites also in the list. So many satellites are in. And then as the beginning itself, space applications, many areas like food, water, how to where to maximize energy, health sector, and then in many areas like sustainable development, like you want to make an impact assessment of deforestation, or what is the type of sources we have, and how we can manage the total ecosystem, climate, how you can predict, and then the weather predictions. Many weather predictions are given in advance. The human lives or the lives, even not only human, even animals, the death number has drastically come down due to this early warning system. There is a perfect tested disaster management system with the coordination of states that will warn and then evacuate people. And then a lot of applications in governance like city mapping using satellite data, and then how to support governments in taking decisions. So we see the application of space for space-based service is increasing day by day. So there is more demand for space applications. Like as well as electronic or e-governance, disaster management, navigation, our own navigation system, remote sensing, weather prediction, communication, telemedicine, tele-education. For a country like India where we have a large areas remote and not well connected, all these new technologies will definitely connect the underprivileged with the available resources and make them feel that they are also, everybody is equal. So we have a very strong application of all these things, and I can say in terms of space application, we have very novel methods, and we are number one among all other countries in terms of applying its the benefits to space. So remote sensing, we have a number of constellations. So we are continuously watching land, ocean, atmosphere, weather, And just one example could be, the potential fishing zone. If you want to say the fishermen where to go and look for fish from satellite data, looking at the temperature of the sea, we can find out where maximum the fish population is likely to come by looking at the temperature or growth of algae or some such bodies which the fish will find as a food. So that way, lakhs and lakhs of rupees government is saving, because now the fishermen can directly go to the place instead of searching the vast sea. They go to the predicted locations, collect the fish, and come back. So there are such novel applications, and we know we have a landmass. Unless we improve the yield per acre, we cannot meet the food requirement. So this is an important area. What is the type of surface wetness, temperature, rainfall, what is the quality of water under, what is the type of landslide, possibility of landslide. All these things are now using satellite images predict, and then many countries, many states are getting benefited by this. As I was telling, disaster management support, we have a near real-time system which will just continuously monitoring whenever, even when you are sleeping, 24/7. Eyes are open and they look at where the low pressure is being developed, to which direction it's moving, and then we give warning, and then appropriately the administration is taking actions. So now it is important, as I was telling, how do satellites orbit Earth? So unless all bodies are attracted to Earth because of its gravity, unless by rotating at a sufficient speed, and the gravitational pull is balanced by the centrifugal force, you cannot stay there. So this is precisely done by a launch vehicle. It is taking it to a altitude, and it is giving a required velocity for that particular orbit. So as you go up and up, the velocity needed to stay in an orbit is less, and velocity should be tangential to the orbit. Otherwise, it will fall back into Earth. So that if you just look at it, a satellite that's going to 400 kilometers has got huge potential energy and huge kinetic energy. So the entire energy is given by the vehicle. Now, if you want to bring it back, a satellite, then this entire energy has to be killed. Just to make a comparison, a 550 kg orbiting satellite in 600 kilometers will have something like 19 into 10 raised to 9 joule energy, both kinetic and potential. So what we do, we make the re-entry body shaped in such a way that during the re-entry phase, that is 100 kilometer and below is the atmosphere, that time 99% of the energy is dissipated by aerobraking because of the friction with the air. And then to protect the body, we will have suitable thermal protection. The thermal protection could be something like ablative, that means it will absorb the heat and disintegrate, or it is radiative, that means it will get heated up and then at higher temperature it will give out radiation. You all know that the black body radiation, something like that, or it could be a refractory type of insulation. So the shape of the re-entry body decides how you remove the heat. So in 2007, we had an experiment called Space Capsule Recovery Experiment, where a 550 kilometer orbiting satellite designed for re-entry, which was made to re-enter and made to splash down at a precise location in near Chennai. You can see it was collected by the Coast Guard. So it was very useful for many missions, like how to bring back, that is how to deorbit and then manage the descent mission. We also did some microgravity experiment. We proved the thermal protection system to protect the satellite and how to do re-entry, and then qualifying many systems like a parachute for space. And then, this has really paved the way for a manned mission, because unless you have a launch vehicle to take man to space and then a re-entry technology to bring them back, you cannot think of manned mission. Now, if you see, there are many types of many countries are involved in space program, but basically USA, Russia and China, they are only involved in manned space program. Fourth country, we are also trying. There are 353 missions with 574 humans from 49 nations have gone to space, including 12 persons who walked on moon in 6 missions. So this is, now we see there are many private firms. And the first person was Yuri Gagarin. And then, of course, he died in a training in 1968. Then the first American was Alan Shepard. And of course, that was the time when Cold War was going on and there was intense competition. And the first man on moon by Neil Armstrong at the end of 1969. Now, if you see, there are many parties, especially in US, like SpaceX, you all know Elon Musk, Boeing, SNC, Virgin Galactic. Many have a manned space program. Many are planning spaceship and Blue Origin. They have a space tourism. That is, they just take it to 100 kilometers and then come down. Something like throwing a stone up, and then the tourist can experience the the thrill of space travel as well as microgravity for a few minutes. So this is one Virgin Galactic flight as well as Blue Origin the capsule. It will go to the edge. This 100 kilometers is called Von Karman line. Just cross it. That is, you are in space, and then it comes back. So while coming back, you can experience just for large glass openings, windows, and it's an exciting experiment, and then feel the. But it is not so. There are interplanetary manned space mission. I hope you know about the Artemis program of the US, where they are planning to have a space station like the International Space Station around Earth. They are going to have a space station around Moon, a manned space station, and that will be a base. From there, they will have a manned program to Moon. And the Elon Musk SpaceX, they are planning to have. You're thinking about having habitation on Moon. Make huge rocket, they land, and then they make habitation. And you can see the space treaties. All the space treaties are even being challenged with the entry of private parties. So this is one area we have to look at it. So it's very challenging to go to space. If you go there without any protection, you will be taken to extremes of temperatures, minus 150 to say plus 150. You cannot survive. This microgravity, radiation is there. And there are so many things. You don't get food. You are isolated from others. You have a very hard vacuum. So there are many challenges. And any satellite in orbit is in a state of free falling. So this, I hope, you should know what is the concept of weight. See, when you are standing on a platform, the platform is giving a reaction on your body. That reaction on your body is the weight. To remove the platform, you are falling down and you are under weightlessness. There is no reaction. So this weightlessness is called as microgravity. Actually, the body is any satellite is falling under 1g, but because it is a weightlessness condition, we call it as zero gravity, which is not exactly correct. So this is Newton's cannon experiment. Probably teachers would have, they would have studied it. He says, suppose you have a tower, and over that there is a cannon, and you launch something at some horizontal velocity. If the velocity is small, you fall near the tower. You keep on increasing the velocity, you fall farther and farther, maybe like this, and like this. But at some velocity, you will find that you are falling and falling, but you will never fall back to earth. But you come and then the body will come and hit you on your back, which is making an orbit. So this is a minimum velocity for this height for any satellite to stay in orbit. So this proves that any satellite is in a state of free fall. It is like free fall, but only thing its velocity is so high it cannot touch. So it's any satellite or a human sitting inside a satellite is in a condition of free fall. Because of that, you experience weightlessness condition, which will create different problems. And then this question is, if humans have to go to space, then they have to be subjected to this microgravity or the weightlessness condition. So one way is to have a drop tower, but drop towers you cannot have human cannot be dropped because of the size. Then second is sounding rockets also will give, but sounding rockets again cannot take such things. But the important is you have a microgravity or the parabolic flight, where the aircraft is going in like a throne stowing up. Its engine will be in a condition where everything is balanced. It is just freely falling from this point to this point. So this is how astronauts are getting tested, like this. So the inside all seats are removed, and it goes on a loop like this. You get 25 to 30 seconds. There you do like flight suit donning or taking food, all those things you do. this is how the astronauts are getting trained. So in space, under this weightlessness condition, many things will happen. The first thing is, our body is having a lot of fluid. All these fluids are pulled down by gravity. The moment this gravity is not there, the fluid will go up, and then the body will get an indication that you have taken a lot of fluids. So you pass on through urination, fluid will be lost. So body will lose fluid, and your body shape with the time could be something like this. And because fluid is coming up, your the face itself can change, and all the vertebrae and the bones will stretch because the absence of weight, and then astronauts can even grow by an inch. This growth or the length change, they consider in their flight suit design. Otherwise, when you are in space, the suit will not match. Of course, space is not a very easy place. There are accidents, many accidents. Many people have lost their lives, especially this one, where the mission was perfectly a successful mission. And when the Russians, when they came back, when they opened the hatch, they found that they are all dead. Till this time, the astronauts were not wearing flight suit. The reason was there was a cabin pressure loss because of inadvertent opening of a valve during the vacuum phase. And then it has become mandatory to wear a flight suit. When they wear a flight suit, even if there is a cabin depressurization, the flight suit can protect the human for nearly 1 hour. So it is now during the dynamic phase, both ascent as well as descent phase, all the astronauts are wearing flight suit. And suppose your body is suddenly exposed to sudden vacuum, then your body can expand. Then many things can happen. Such things are tested in a decompression chamber, and astronauts will be put, and the pressure will be depressurized. In fact, there was an accident where a technician was subjected to a very low pressure for over 1 minute. That is the only incident where a person was subjected to more than 1 minute of vacuum, but still he came back, although he had many injuries, but he survived. Now, this is our Gaganyaan program. You can see the Mark III with the human-rated vehicle. And the Gaganyaan program is to go to 400 kilometers with 3 crew. And this is the orbiting module. This is the crew capsule and service module. This will come back. And this is the conventional Mark III. This is modified like this. This is an escape system. That is, in case anything goes wrong, the crew capsule with the crew will be taken away by the escape system by firing just for multiple solid modules that will very quickly take the crew away. And just for scale comparison, this is the crew habitat, and this is the service module. And it has got so many systems packed inside. There are seats, it's a pressurized cabin, life support system. It has got eco-friendly green propulsion. It has got navigation, guidance, control, so many systems, avionics system, debris protection system. So all these things will be placed inside this. So we need, if you want to go, we need to make the system human-rated. We need a high reliable escape system. We have to go for very safety features at launch pad in case any propellant leak or something. There will be safety bags and other things where crew can escape. Vehicle health management system, we need redundant systems. So a vehicle has to be totally revisited if you want to have the Gaganyaan mission. So this is how we modified the Mark III into this by making many changes in propulsion, avionics, control system, pyro. But still, whatever you do, still a vehicle is a complex system. So the best practice is to have an escape system with a very high reliability. And this is the Gaganyaan mission profile. It's like any other satellite, where the capsule will be injected. It has got solar panel. After the orbital phase, you deorbit, come back, service module is separated, then aero braking, parachute, and splash down in sea. So, depending upon the shape of the body and its lift to drag ratio, you can, through the atmosphere, you can take any type of trajectory, and then acceleration, heat flux, etc. can be managed by manipulating the lift vector. And this is how from Sriharikota, when it takes off, it is the ground trace, and everywhere where along the track we will have many teams of recovery ship in case of any anomaly. If the crew is boarded and then they fall into sea, they will be recovered. a nominal mission, you will be landing near Port Blair, or in case you want an alternate landing, there is another point. So this is how it is planned. And we had a mission in 2014 where a full-scale capsule was taken to 125 kilometers and just splashed out. It is called a crew module atmospheric re-entry experiment, where thermal protection, parachute, control, all these things got tested. Similarly, you can see the capsule with its locating dye. This will release a dye which can be easily seen by an overflying aircraft and locate, in addition to electronic beacons and other things. Second is the escape system. The one situation is at launch pads, there is a propeller leak or something. Then you fire the top portion. This part also we have tested in 2018. You can see propulsion system, escape system is fired, and then the capsule is released, parachute is deployed, and it has come back and landed. And now we are going to do more escape system tests this year by taking it to a higher altitude with a small vehicle. This is called a test vehicle. This will take it to, say, intermediate. What we have demonstrated is at launch pad. Now, during the ascent phase, because the initial condition will be different when you abort during ascent phase, that will be demonstrated by a test vehicle. So it's important when humans are there, we talk about the comfort, ergonomics, reach, and their all sorts of things. So we do such things and see that is the interior is convenient. At the same time, the type of vibration that is acting on the human, especially human body has got all critical frequency less than 10 Hertz. So we need to ensure that no critical frequencies are activated. And at the same time, the way we are orienting the crew, see, depending upon the way crew is sitting, the G tolerance can be different. So the way if they lie like this with the chest normal to the acceleration acting normal to the chest, we can take high G for short duration. So the crew seat is always oriented like this so that they can take high acceleration. And so it's important what is the type of acceleration, duration, and what is the impact on crew, especially on the neck or when it is impacting in different directions, what is the type of crew injury criteria. So these are all we are working out in consultation with the Institute of Aerospace Medicine under Air Force. They have pilot training data. So these are all being worked out, and it's important that the seat is also very carefully planned to take maximum acceleration as well as deceleration. And the impact attenuation system, when the seat is landing, when a cat is landing, it is not landing with all the four legs. It lands in two legs and then secondly, back legs. What it does is, it is spreading its peak load into two peaks, polar peaks, thereby the injury is minimized. And from this biologically inspired design, even crew seats are being designed. Instead of landing with, simultaneously, the loads will be distributed sequentially. Now we know that there are hundreds of thousands of micrometeoroids in space, human, man-made. These are all high velocity particles flying at 7 to 15 kilometers per second. But they are all more than 10 centimeters. We have tracked, we know where they are, we can avoid. But below 10 centimeters, they come and hit, can create opening. So our design is in such a way that just got two walls. The first one will take care of the first impact, then it becomes a debris cloud, and it is energy spread over a large area, thereby protecting the second one. So this concept you have tested, and this capsule or the orbital module will have a meteoroid protection system. And similarly, the space radiation is another threat. But space radiation, we are not worried for this mission because we are inside the capsule. We have measurements. But when we go for extra vehicular activity or interplanetary mission, we need data. What is the type of radiation? What is the mitigation plan? So then, similarly, the life support system. If you want to have an atmosphere like this, we need to have a oxygen supply, carbon dioxide removal, and humidity removal, pressurization system, partial pressure of oxygen. All those things happen in Earth without our knowledge because of this solar, what you call as this cycle. But when you want to mimic the photosynthesis inside a crew module, it's a big task. So we have a different system. There is a cabin pressure control system that will control the pressure. There are thermal and humidity control system that will give you air conditioning, carbon dioxide removal system, flight suit, food, water, fire detection. So many subsystems are integrated into this. I can say this thermal and humidity control system is now getting tested for integrated way. You can see the cruise mode, which is getting tested. As well as flight suit for the first mission, we are procuring it from Russia. Our astronaut candidates, they have gone there, they have taken the dimension, because this is a high reliable system, flown more than 200, 300 times. So our crew from Indian Air Force, through a selection process, test pilots from 60 number, we have zeroed down to 4. They have gone to Russia, where they have undergone the preliminary training for 1.5 years. They have come back, and Bangalore, we have the astronaut training center, where virtual reality training simulators we have made, and they are undergoing training. This training facility is inaugurated. And similarly, the recovery is also a national program. The Indian Navy is interested with that, but many agencies are part of it, because we need many resources to take care of recovery from multiple points considering about. And we have 28 proposals from all over India. There are some 5 experiments shortlisted. And again, I have a request to all the teachers, if you have a wonderful idea, we have many microgravity platforms. If you can make payloads, we can fly. In fact, PSLV, PS4, the final stage, we are converting into an orbital platform after the satellite is released. So that can be used for experiment. And also we have a humanoid in our first mission, because we know if you want to have meaningful space exploration, man alone cannot do. We need humans also, humans with AI-enabled robots, which can take command from man and then do things. A complementary role for robotics, so a parallel stream. We have a robotic system, which can see robots can take care of satellite service, debris clearance, or if you want to have extremely hazardous environment like a Martian atmosphere or there, we can always use robotics systems. And if you want to do some manufacturing operations, so it has got multiple application when we embark outside the Earth into farther places like say Moon or Mars or asteroids. So with that, I conclude my speech. I hope I was clear to you.